One of the first things you're generally told in GCSE is what is a property of a chemical reaction, and you say it's not reversible. And do you remember if you did the OCR, I think you cook an egg, don't you? And you look at the protein and you say this is a chemical reaction because it's not reversible. You can't take the egg white and change it back into the original egg. However, many chemical reactions are reversible. And we show that they're reversible by using this little arrow here. So what is this telling me? Well, it's telling me that I can take sulfur dioxide and react it with oxygen to make sulfur trioxide. But equally, sulfur trioxide can split apart to give me sulfur dioxide and oxygen. Now this topic, we call that an equilibrium. It's an equilibrium reaction. And it's dynamic. What's happening is if I start with my little box, in order to get a dynamic equilibrium to work, the first thing I need is it has to be a closed system, which means I have to contain everything in a box. I can't let things escape. If I start in my little container with just SO2 and O2, they're going to start reacting and I'll start building up SO3, won't I? Yeah. So SO3 molecules will appear. But initially I haven't got very many SO3. So what could we say initially about the rate of the forward reaction compared to the backward reaction?
Equilibrium is to the...
Well, if I start off, I haven't got any of that. So what can you say about the backward reaction? Is it? There's no gap. So how does the rate of the backward reaction compare to the rate of the forward reaction? Yeah, this one's fast, isn't it? And we can use that based on our rates of reaction. Initially, what can we say about the concentration of these two compared to the concentration of that? We've got lots and lots of this, haven't we, when I mix them together, but not a lot of that. And we know that rate of reaction is affected by concentration. So initially, that is fast, and that is slow. But, so I'm making more and more of SO3. So the concentration of SO3 increases, so what's going to happen to this rate? It gets faster, and this one's going to get slower as that one gets. And eventually we reach the stage where the rate of the forward reaction is the same as the rate of the backward reaction, and that's when I've reached equilibrium. So if I measure the concentration of SO2, O2 and SO3, they are always the same. So I can wait for hundreds and hundreds of years, nothing will change once I've reached equilibrium. So there's points we need to know about what a dynamic equilibrium actually involves. Okay, so using that example, let's say what do we need? We can say a dynamic equilibrium exists when the rate of the forward reaction is equal to the rate of the backward reaction. There is no overall change in the macroscopic properties e.g. temperature, pressure, or concentration. You must have a closed system in order to reach equilibrium. Why do I need a closed system? Well, if in my little pot I've got SO2, O2, SO3, something like that, what will that ever reach equilibrium? Things can just escape, can't they? SO3 can escape and so on. So I will never reach dynamic equilibrium if I've got an open system. It must be a closed system. Now, we said there's no overall change in the macroscopic properties. So, the concentration of SO2, O2 and SO3 stays the same. However, the molecules are different. So they're not always the same. So how does that work? Well, if you think about, if you've got, say, Bournemouth, like so, in the mornings, you get quite a few people travelling in to Bournemouth, don't you? Because they're all commuting in for their jobs and so on. And not many people going out. So the rate of forward going in is much higher than backward. But at some point during the day, you reach equilibrium where you have the number of people going in is the same as the number of people going out. The people are different. It's not all the same people trapped in Bournemouth forever. That would be scary. But you do have, so if I counted up the number of people, it would always be the same. However, the people themselves would be different. I've reached dynamic equilibrium. People are still moving around in and out of the city, but they're not always going to be the same. And I have to have, in chemistry, to have a closed system so that my chemicals can't escape.